These are the solutions to VCAR worksheet number 3. Example 1. Part of the graphs of the function y equals a on x plus b all squared plus c is shown here. The values of a, b, and c respectively are. So what we know is that a would be a dilation factor, b is an asymptote, and c is also an asymptote. We can see that the whole graph has been shifted to the right by 1 and up by 2. So I can already tell that my graph is going to have the form x minus 1 all squared plus 2. And then in order to be able to find a, we then need to substitute in a value. So let's just see if any of them work with what we've got so far. And if there's more than one option, then we can go ahead and find a. So I can see at this point, because b is plus b right now, we are going to need b to equal -1 and c to equal to 2. Let's see if there's any options there. So I can see that here are the ones that have -1, c is 0, and for option B, C is 2. So it doesn't really matter what the specific Y value is in this case, because there's only one option that has this B and C. So in this case, it has to be B. And just to completely confirm it, we can see that A is going to be that of a negative value. So we can see that our truncus is also negative, just to confirm. Question 2. The graph of y equals x minus 2 on x plus 3 has two asymptotes with the equation. We can't really tell what the function is from this point. You can go ahead and use your CAS calculator if you like, but the easiest way to do this is to long divide so we can actually see what the function looks like, which would be a hyperbola. So whenever you've got anything of this form, we just divide it through. X goes into x one time. 1 times x is x. 1 times 3 is 3. And then we'll go ahead and subtract. X minus x is 0, which is what we want. And then -2 minus 3 is going to be -5. So what this tells me is that I've got one whole, and then I've also then got -5 as a remainder. And when we have a remainder, we always write it over our divisor. So this is going to be our hyperbola, and it's in a particular form where this is going to be my x asymptote. So my x asymptote is at -3, and this will be my y asymptote, which is at +1. So again, having a look at which option works. So that'll be x is -3 and y is 1. That gives me C as my only option. For example 3, we have the graph of this function where D is the maximal domain and it has asymptotes. So once again, you can, it's very similar to the previous question. So you just do the exact same thing. We're going to go ahead and divide it through. I'm just going to write it in this particular form just to make our life a little bit easier. So x goes into x -1 times. Then -1 times -x is going to be +x. -1 times 2 is going to be -2. And then exactly the same as before. -3 minus -2, which becomes +2, is going to be -1. So in this case, I've got -1 wholes. I've got a -1 remainder over -x plus 2. But you have to remember that in order to see the true translation, there should be no numbers in front of the x. So the asymptote is actually at x is equal to 2, because when I take that negative out, I can see that there has been a translation in the positive direction of the x-axis. So my asymptotes in this case are going to be x is equal to 2 and y is equal to -1. So again, just finding which option that works for. That's x is 2, y is -1. That looks like it's going to be D. Example 4, we've got this particular equation has only one solution for x when w are these particular values. We have already seen this question in worksheet 1, so hopefully you remember it from there. But if not, we kind of want to think about, well, what does w do? W is a vertical translation. So the idea is that if I can graph just this graph here, I can figure out how many solutions it already has, and then based on the value of W, I can move the graph up or down in order to only have one particular solution. So if this is going to be some sort of a cubic, because it's to the power of 3, say it looks like this, what we can do is we can move it in a way such that there would only be one solution if I moved it a particular value up, or likewise if I move it a particular value down, when it crosses only once on this side, then there would again be only one solution there. So let's go ahead and find out what that is. We're going to use our CAS for this function, for this question. So please pull out your CAS. And we'll go onto the calculator page. Actually, not the calculator page. We need a graph page. So that will be x to the power of 3 minus 9x squared plus 15x. So if I just graph this without the w, I can see what the function looks like, and we can zoom out enough to be able to see the whole function. And so as we just said before, we can see that the function has currently 3 solutions, but if I move it up or down a particular amount, it's going to get to a point where we're only going to have one solution, where there's only one part of the graph that is crossing through. In order for us to figure out what that value is, we should find what the maximum and minimum values are, because it's those turning points that's causing us to have more than one solution. So I'm going to go to, not the zoom, I'm going to go to instead the analyze. So that will be option 6, I think, on your CADs. So it'll be analyze, we'll go to maximum. So let's find out what this first maximum is. That's at 1 and 7. That just zoomed in a very funny amount. Let me try and fix that up. I'm not sure why it zoomed in like that. Let's try that again. So we've got maximum, that's 1 and 7. And then we'll try and find the minimum as well. So that's 5 and negative 25. So I'm just going to go ahead and draw that on the other page just to make it very clear as to what we're doing here. So I've got this particular function. It's doing this. This was at 1 and 7, and this was at 5 and negative 25. So the idea is that if I were to move this function 7 down, because this value here is 7, if I were to move that 7 down, can you see how if I move it more than 7 down, there will only be one turning point left. So what I could see is that w must be greater than or equal to negative 7, or rather, sorry, less than. Because if I move it negative 7 down exactly, so if I move it down exactly 7, then I'll have 2 solutions because I've got this and this. So it has to be at least less than negative 7, as in it could be negative 8, negative 9, whatever it is, so that it goes below the axis, that turning point. And all that's left is this part above it. So that's our first part there, that w must be less than negative 7. So I need a number that is less than that in order to drag it down more than 7. Next, the other option that I have is that I take this up. So in order for me to get this onto the axis, I need to bring it up by 25. But of course, if I bring it up only 25, then I still got 2 solutions. So I need to bring it up at least 25 or more. So that's why w needs to also be greater than or equal to 25. So putting that together gives you option D. Okay, example 5. The graph of f of a function f with the domain R is shown. The graph which best represents 1 minus f2 of x is. So we need to recognize what are the different transformations that have happened here, and there's 3 of them. So firstly, I can see that there is a dilation by a factor of a half from the y-axis. You have to remember that when it's on the inside, when it's attached to the x, it's always the reciprocal. And when we did mapping, you would have seen why that is the case. So it gets flipped. So if it's from a half from the y-axis, so we're starting at y and then we're moving away from it, or rather inwards this time, what I can see is that my graph should become squashed. It should become half of the size that it currently is in this direction because it's from the y-axis. I can also see that I've got a reflection in the x-axis, and I can also see that the whole graph has moved up by 1 unit. So just observing, I think that the easiest place to start off with is always a reflection. So we want something that is reflected. So not doing this, rather we want it to do this. So we can already start to eliminate a few of them. There's no reflection here, and there's no reflection here. So it can't be B or D. Next, as we said, we want to see a graph that is half the size. So for example, this one looks like it's larger. So here we had the x-intercept at 1, now it's at 1.5. So it can't be this one. And this one does look like it's become smaller, but it doesn't look like it's small enough, or maybe it's just a mistype because the intercepts are still going through 1 and 3. So nothing has really happened there, only a reflection, I think. So the last one, this really leaves only one option, but you can kind of see all the features that we were talking about. This does look like it's half the size of this. And just to confirm, our x-intercept is now at a half rather than it being at 1. And then the other thing is that we had the y-intercept being at 3. When it gets reflected, it will be at -3, but remember how it's moved up by 1. It should now be at -2, which indeed it is. So the answer to this question would be E, and you can do it either through a process of elimination or just sort of considering all of the transformations happening at once. All right, example 6. We've got the graph of this particular function. It's reflected in the x-axis, and then it's translated 3 units right and 4 units down. What's the equation of the new graph? Because there's no dilation, I would probably suggest to just go ahead and put your transformations in. When there's a dilation or when there's a reflection in the y-axis, that's when I start to like to do mapping, because it's just very easy to make a mistake. But when it's just a reflection in the x-axis, remember in the x-axis is always on the outside, so it's negative f of x. And then translations, they're quite easy to be able to just recognize. So a reflection in the x-axis would look like this, and then also our translation if we've got 3 units to the right. So we'll usually go -3 and 4 units down. So we would expect it to then be -4 down. You do need to make sure that the order is very important. So for example, if they told us we first moved to the right and then 4 units down, and then we had the reflection, we would actually expect for it to be a +4, because we would move it 4 units down, then we would reflect, then we would take the negative of the entire equation. So again, if you're unsure about the order, I would map it. But it's just because this one happens to have a very straightforward order. First you reflect, then you translate, and that's all that's going on. That's when you can kind of just have a look at the function and confirm what has happened. But otherwise, I would map. Okay, example 7. So we've got the point P for -3 lies on the graph of a function. The graph of f is translated 4 units vertically up. So we're going to have a +4 at the end of the function, and then it's reflected in the y-axis. What's the coordinates of the image? So in this case, I would probably actually sort of start our mapping. So when we try to map, I like to write my coordinates out like this, and then write what's going to happen. So if the graph of f has been translated 4 units vertically up, that means for every y value we're going to add 4, and then we've got a reflection in the y-axis, which means every x value we're going to multiply by negative. And that's all that's happened. So the reason that I write it so spread out is in case there's a bit more that's occurred, but in this case, that's pretty much it. So our new x and new y is going to be -x and y +4. And now all I need to do is simply substitute in this coordinate. So we would have -4 and then -3 +4. That'll be -4 and 1, which would be A. All right, next question, example 8. We've got the graph of y equals kx minus 4 and intersects that particular graph at 2 distinct points 4. So whenever you see this idea about 2 graphs intersecting and they want to know at specifically 2 points, what are the alternatives? The alternatives is that they could intersect at 1 point or at no points. And whenever I'm thinking of this idea of 2 solutions, 1 solution or no solution, I'm always thinking of the discriminant. Another reason I'm thinking of the discriminant is because it's between a quadratic and a linear, and when I make them equal to each other, it forms a new quadratic. And how do we know about how many solutions with quadratics? We think of the discriminant again. So we're going to make these 2 functions equal to each other. I'm going to take everything over to one side, and I'm going to make it into the form of ax squared plus bx plus c. So what that means is I'm going to factorize the x out, and I'll just write the coefficient here. That'll be 2 minus k plus 4 equals to 0. Now, in order for us to have 2 solutions, that means the discriminant must be greater than 0. So first we're going to go ahead and find the discriminant, which is b squared minus 4ac. And we want that to be greater than 0. So I might go ahead and expand this. So that'll be 4 minus 4k plus k squared. And then -4 times 4 is going to be plus 16. Sorry, rather negative 16. I want that to be greater than 0. And I'm just going to rearrange it so it's in the form of a quadratic. So I have k squared minus 4k, and then 4 minus 16 is going to be -12. Now, when we're trying to solve an inequality with a quadratic, there's only one way to do it, and it is to sketch this function. And in order to sketch, I need to find the two x-intercepts. So what I need are two values that will multiply to give me negative 12 and add to give me negative 4. And those two values that I can think of are going to be negative 6 and positive 2. So just trying to make more space for myself. If I graph it over here, I'm going to end up with k is equal to 6 and k is equal to negative 2. And there's my quadratic. And so what I'm looking for is, when is this quadratic greater than 0? And if you remember our three regions of our graph, this is where all of our y values, or rather this time it's our discriminant values, are positive. On the line is when our y values are 0, discriminant values, sorry, and then below are when our discriminant values are negative. And because I want it to be positive, I'm looking at all of the values where it is above the graph. So that's all of this section here. I can shade all of that in. What are the corresponding x values that happens at? Well, it's from the x-intercept, not including though, because at the x-intercept it's 0, and onwards. So that's what corresponds to the shade. So I can see here that means that k needs to be less than negative 2, or k needs to be greater than 6. And when I have a look at my options, it gives me B. So that's how you complete these kind of questions, and they do come quite often in exams. It's a very popular multiple choice, even though it looks like it definitely takes more than a minute to do. It's something that you just need to practice and get faster at, because it is quite a popular multiple choice question. Okay, next question, example 9. Hopefully you remember from your previous worksheet that all of your values in here need to be negative. The reason for that is because even though I know this intercept, for example, if this were negative 2, it would look like x plus 2. But the reason that we don't choose a positive in here is because b itself is a negative value. So I need my general bracket to look like this, so that when I insert b is negative 2, it ends up becoming a positive, which is what I want it to end up with. So in general, inside the bracket must always be a negative value, unless they specifically tell you that b is a positive value. Then that's when you can include a positive. But in general, when they're asking for rules, it'll always be a negative. So I can already eliminate so many of them. Anything that has a positive, that can go, that can go, that can go. So it's either C or D. And then I can see two features. First of all, at C, it is a turning point at one of the intercepts. So that means I know that it must be squared. So I can already tell that it's C. And another thing is that this is a quartic, but it's a negative. So I also expect for there to be a negative. So that's a quick way to be able to eliminate to get the correct answer for this question. All right, question 10. The transformation that maps the graph of y equals that onto the graph of y equals that is... so there's a couple of different ways to do it. You can do it through a shortcut method by just kind of thinking about, all right, well, how do I get from 8 to a 1 in front of it? But that can be kind of confusing, can also lead to errors. So I find the easiest way to do it is to map, just to make sure that you're doing it correctly. So in order to map, we have our old function and we have our new function. Make sure you put your dashes into your new, because remember, to figure out what's happened is we want our new to equal something to our old, because we want to understand what has happened to old x to lead to new x. So that's why it's really important to include your dashes. Nothing's happened to the y's, so I can just leave that alone. We're just going to equate the x's so we can see what's happened there. Now, I know that usually we don't write the cubed, but that's only because they're in brackets usually. So cubed, you can just equate the inside because it looks the same. In this case, it's underneath the square root. That's what's in common. So anything underneath the square root is what needs to be equated, because it's not the same in this case. The ones are the same though, so they can cancel out. And then the next thing that I might want to do is take the cubed root of both sides. So then that will end up being 2x is equal to x dash. And that's exactly where I want to get to. So what this is saying is that the image is equal to 2 times the old x. So what that tells me is that there was a dilation of factor of 2 from the y-axis, because from the y-axis is what affects the x values. So that would be A. All right, last page, example 11. The graph of the function f is obtained from the graph of a function g with that particular rule by reflection of the x-axis followed by a dilation from the y-axis of a half. Which one of the following is the rule of the function f. Now, of course, you can go straight in, start putting in your values, but I can see that there's a dilation from the y-axis, which always worries me a little bit because I know that it's easy to make errors. So in this particular case, I might map it because that's just, more confidence in terms of making sure I get that correct. So how do I get to my new x and my new y? Well, what has happened is that there was a dilation from the y-axis, which means affects the x values of a half, and then there was a reflection in the x-axis, which means that affects the y values. So I get x dash is equal to a half x and y dash is equal to negative y. And because we're substituting it into this old function, I want to get old x and old y by itself in order to be able to substitute it in. So x will be equal to 2x dash and y will be equal to negative y dash. And now I can go ahead and substitute it in. So old y into old y and old x into old x. So we'll go negative y dash is equal to the square root of 2 and then 2x dash minus 5. We'll simplify the bracket first, so that's 4x dash minus 5, and then finally I'm going to take the negative over. So the correct answer should therefore be D. So you can see, if you feel confident, go ahead absolutely and just chuck those transformations in, but for me personally, I just find it a lot more reassuring to know that this is going to be the right way to do it. All right, finally, for our short answer, we've got on the axis below, sketch this particular graph, label all the axis intercepts, and label each asymptote with its equation. So it doesn't seem like a transformation question, but the idea is that it's a hyperbola in this case that has experienced a transformation. So first up, we'll draw our set of axes. It's not quite even, never is with these. I think even if I put it here, looks a little bit better, but not that much. Anyway, what can we see has happened? We've got a dilation of factor 4, which doesn't really affect the way that the graph looks, but it will affect the actual value. So it'll affect my y-intercept when you go ahead to put it in. We've also got an x-intercept, asymptote of -1, and we've also got a y-asymptote at 2, and of course we need to not forget we do have a reflection there as well. So let's start off with the asymptotes. X is -1, so I'm going to go ahead and put that line in, and y is 2. And then I might find my intercepts. So the first thing I'll start off with is the x-intercept. I'll make y equal to 0. I'm going to take that fraction over to make that positive, and then I'll swap the denominator and numerator. So that's 4 on 2 equals x plus 1. That'll be 2, because 4 divided by 2, and then I'm going to take the 1 over. So x is going to equal to 1. So that'll be 1, 0. And then for our y-intercept, we're going to make x equal to 0. So that'll be y equals 2 minus 4 on 0 plus 1, which is just 1. So that'll be 2 minus 4 is -2. So that's how we can see the dilation from that -2 there. And then all we simply need to do is draw in our hyperbola. Remember that there has been a reflection, so our original hyperbola looks like this, whereas our reflection is going to then look like this. And it's quite obvious that it does that given our intercepts that we have. So remember to approach your asymptote, but you can't touch the asymptote. So it'll look something like that. So that's 4 marks. I would say you'd have 1 mark for the asymptotes, 1 mark for the shape, and then perhaps 1 mark for each of the intercepts. That's it for this worksheet. If you have any questions, please make sure that you ask your teacher.